Hello everyone. Thank you for joining this presentation, and thanks to the organizers for the opportunity. My name is Jakov Petrina, and I am currently a firmware engineer at Certura. And today I will talk a bit about the work we have been doing with embedded Linux platforms. More specifically, I will talk about our system for building operating system images for network devices, and this system is called Replica One. Okay, so first let me give you a bit of background information about the kind of work we do. So we are a company based in Croatia. We provide a range of software engineering services, and these services span from low-level board bring-up stuff, like for example in the Linux kernel and the U-boot. Also, we do driver support and these kinds of things. We do user space software development as well, and we focus here mostly on embedded use cases. And we also provide cloud solutions, so for example, device management and so on. Basically, our approach is to provide high-quality open source solutions, right? Basically, we use open source projects, and we basically want to contribute with features and improvements so that our clients can actually use them based on their requirements. Our main aim is basically to bridge this gap between open source and the enterprise, right, for our customers. Like I said, we are basically focused on open source support for network devices, and these are generally embedded systems, right? So think about routers, access points, network switches, servers, and so on. And as part of this work, we are actually quite active contributors to a range of open source projects. So think upstream Linux, U-boot, systemd, and so on. We've been active in the community. We try to work with upstream to kind of like develop new features and improvements based on what our clients actually need. So what are we actually trying to achieve regarding these operating system images on network hardware? You might have seen the term network operating system, but why is network hardware that special, right? And how do you exactly build these operating system images, and what should be a part of it, right? So there are some existing open operating systems that target these kinds of hardware, so networking. OpenWRT is actually a long-running distribution for CPE devices, so access points, routers. We actually have some relatively new work and initiatives in the network switching domain, like Sonic and DENTOS. I only mention these examples for an excellent overview of the state of open source network switching. I would highly recommend the Paul Menzel's talk, which was yesterday, at this conference. And Paul spoke a lot about the challenges we face in this domain. Basically, the short answer is that the situation is fairly similar to what's been going on in the proprietary Linux graphics driver stuff. So basically, some chip vendors wish to keep things close to their chest, right? But in the meantime, we have something to work with. We have some platforms that actually function as open network switches, so we're focused on that, and maybe in the future a fully open switching platform might happen, right? Okay, so with operating systems for networking hardware, as you have seen, there's a lot of diversification. So each of these operating systems work for individual category of devices. So OpenWRT, for example, access points, routers, right? Each of these might have their own specific way of doing things, like, again, OpenWRT. They're fairly involved because they do process management their own. They do network configuration, especially. They configure wireless interfaces in quite complex way, and so on, right? And basically, our main goal was to try and unify these kinds of network devices, so to have a single platform for access points, for network switches, for network servers, maybe even virtual machines, and these should all run the same system, and they should be built in relatively the same way, right? But in our experience, we think that we really need quality open source support for this. It means quite a lot. Basically, when we do board bring-up work, we found that it's much easier to work with upstream, with the community. We want to upstream all of these patches rather than to have them out of tree. OpenWRT might, for example, have a lot of patches for individual devices, but we actually strive to have them merged upstream so that we can lower our maintenance burden, right? And obviously, upstream has quite rigorous quality standards. So this is our main focus. And obviously, we have to be able to easily integrate different kind of value-added software, right? So basically, we want packaging of the software to be easy, and we want to define configuration to be as easy as possible, so that we define a whole OS in a few simple steps, right? So building operating system images might seem simple. We take some source code. We basically, it can be either the kernel source, it can be userspace application source. We basically configure it by enabling and disabling a couple of features. We set some compile time flags and so on. This mostly policy, right, specification. We might need OpenSSH, we might not. But the build process is actually where the magic happens, and this is the most complex part, I would say. We basically build their cross toolchains and cross compilers to actually cross compile and build OS images for different architectures. We might not need to do this, but for these kind of network devices, we usually do, right? And obviously, we have a lot of build dependencies. These kind of things can get quite complex. And after this build process is complete, we have already, it can be a file or it can be several files, but we consider this to be an OS image. For embedded devices, you would call this firmware, right? And flash it onto the device. And this process, the whole process is where kind of we need something new, right? We need some kind of paradigm shift. Basically because it seems simple, it can get complicated, especially if you have like network switches, which have their own specifics, like ASIC drivers and so on. And basically, these systems that exist today did not really fit our needs and our requirements, and this is why we set out to create Replica One. This is an open source build system. It is designed to build operating system images, but for all kinds of network devices. And this project has been ongoing for quite a while now. Our initial public release was in 2022, in January. It is currently based on Gen 2, more specifically the Gen 2 Sportage, or the package manager. The system has been continuously upgraded, advanced, with support for new platforms. Initially, we had support for Delta switches, which use Marvel silicon, but we also expanded to some Mellanox, or now NVIDIA hardware, IE, II, and Method devices as well. Obviously, these are switching hardware, but we also support like IPQ platforms, which are access points, and so on. As part of this work, we've done a lot of upstreaming. For example, board support code for the Delta platform has been pushed upstream. We did some work on the DHCP leases in Systemd Network D. We worked on wired 802.1x authentication. We also did that for DentOS as well. This is part of the host APD stuff. We haven't upstreamed this, so we'll see how to work with the community to have that upstreamed. And as you can see, our main focus is on network hardware, but obviously this system can be used for any kind of generic operating system images. Network hardware especially because we actually build operating system images that kind of like are long-lived. They aren't considered to be upgradable via packages that much, right? And we can just place everything we need and have them deployed for a long time, right? So basically, the main topic of today's talk would be about our roadmap. So as you can see, we are actually planning to switch over from Portage to Spack, and I will talk about this in a little bit. So our main objective right now is to kind of define OS image components in some kind of scripting language. This system should support building images on multiple platforms and distributions. Right now we are using Docker, and Docker is a pain for some bit, right? Some other build systems also use Docker, and we're trying to transition from this to work natively on individual distributions, right? As part of this approach, we have actually evaluated different package manager concepts, right? To integrate as core of the system. We have evaluated these port-style package managers. These go way back, like BSD ports, and Portage is also a kind of like a spin-off of that. But we also looked at modern kind of like functional package managers. You might know about Nix. It's quite recent, quite interesting. I think new Wix is basically very, very similar to Nix. And as I mentioned, we've focused on Portage initially because Portage is quite a good fit for us. It has a very flexible configuration space, right? They have like support for disabling features via use flags, and we wanted some kind of alternative to this. And this is where I can show you a bit about Spack. So, is this? Yeah. So after evaluating all of these kind of package manager solutions, we even thought about making our own, but it's a lot of work, right? And we came across Spack. This is actually a project out of Lawrence Livermore National Laboratory in California. They have been heavily involved in scientific computing. This is where the project comes from. I've cited here a paper by Todd Gamlin, and they define a lot of theoretical background for Spack. For example, using these answer set programming for dependency resolving, and this is where specific terminology for Spack comes from. Like they use the concept of a concretizer, which I think you might find definitions in this paper quite interesting, right? So the package manager, in community's own words, is basically a flexible package manager, right? That supports multiple versions, configurations, platforms, and compilers. It's important to note that this package manager was not originally conceived to build an OS image, right? It runs on the system parallel to existing package manager. but it has been designed for large supercomputing centers because scientific code bases can get quite complex. They have a lot of requirements. They need to build with specific compiler options, specific versions of packages. It gets quite messy very fast, right? And this package manager is actually very similar to Portage. It's actually inspired by Nix as well, if I understand correctly. And we think it might be a good fit, right? And this is how Spack can be used to build and install packages on the system. So, for example, here we are installing MPLX package. We are doing this in the command line, but we can specify many different options. So, for example, we can use custom versions, custom compilers, enable, disable different options, compiler flags, and even set target architecture. This is very related because we want to kind of like optimize for different architectures than the system we're building on, right? This is basically very similar to how Portage does things. Portage also supports this via use flags, so it's fairly similar, but we think Spack is much better fit for us based on some other requirements, right? So so basically we can specify quite a lot, but it's important to note that everything here is basically written in Python, the package specification, right? The recipes, build recipes, and this is a special Spack syntax, right? Some kind of domain-specific language in Python. And actually, here's an example of a Spack package. This is for the bash package, if I can see. So yeah, basically, sorry for not providing a syntax highlighting though. But as you can see, we define a few important parts like versioning, dependencies, dependency versions, right? And then afterwards, we actually define how to configure the package during the build process. We configure how it's going to be installed and how to check whether the package is built correctly, right? And this reminds me very much of Portage recipes or even Arch Linux PKG builds, right? So some other notable features of Spack. They are mostly function of its like theoretical design, right? So basically, during the dependency resolution, the system, the concretizer, resolves a DAG problem, right? A graph problem, and it can use a lot of this information to basically ensure ABI compatibility. This is quite important in scientific world because there's a difference. If there is a difference between ABIs, you could have like drastic performance issues and so on. It can also guess some details if the user is not explicit, so maybe best options to take. There's also some kind of hashing in the DAG so that build specification can be written much more easily. Basically, you do not need to do any kind of hacks with like trying to find a library. The whole Spack environment kind of like does that for you. Also, the community provides public binary cache, so with pre-built packages, which is quite useful to get up to speed. And I think this is quite interesting. Portage, I think, does not yet have, or maybe they do. I'll have to ask our colleague who is a Gentoo developer, but basically the idea is to have like pre-built packages so you don't have to build everything from scratch, which might take 4 hours or something like that. And so Spack is great, and we actually want to use it as a basis for our build system, but where are we right now? The community, Spack community has been hard at work. They have been working on several key features which are important for us when considering this work. First of all, we require the build dependencies of each individual package to be modeled in DAG, right? This was not the case, at least not before a recent pull request. Basically, they have to be built separately because Spack would otherwise use dependency from the host, which we don't want to use. Next, we want compilers to be modeled as dependencies and actually built by Spack. This is also not the case right now, but will so in the future. And this might actually complete the whole system. So you would have Spack building a cross-compiler, which would then build the rest of the system. Currently, like I said, this dependency work has been merged upstream. This allows us to work on getting libc modeled as a package. And this, after libc, everything else comes into place, like systemd, the init system, and then the rest of the user space applications. Basically, we have some prerequisites to get this working, and the final result will be an operating system image, right? And we are working with the community to get this packaged. They are interested in this kind of work, and we'll see where we get. So, like I said, the Spack community has been quite active. They have been working on the v0.21 release. This release will feature, if I understand correctly, this merged pull request for separate concretization of build dependencies. This was a requirement for us, and compilers to be modeled as dependencies. This is still a work in progress. During this development effort, we will work on testing these Spack builds for embedded devices, more specifically, especially obviously the parts which concern themselves with cross-compilation. Basically, this is packaging work. Gentoo has a lot of kind of like specific cases where they need to resolve issues when it comes to cross-compilation, and obviously the Spack has not been used in that way right now, but with our help they will. So we're trying to engage the community during this process with mutual benefit, and the community is quite active on Slack, and we are attending the weekly telecom meetings to discuss these with them, right? So, all in all, what to take away from this is that we need some kind of system which is aligned with open source communities and upstreaming. The system needs to be relatively lightweight and does not need to have like any specific dependencies. And it actually can function as an open source, some kind of ecosystem, right? The idea is to kind of like unlock markets which are currently dominated by proprietary solutions, right? And for additional resources, you can check out these links. But I think I'm done with that, and thank you everyone for listening. I think we have time for questions, so please go ahead. Sure. The mic is here.
Yeah, take the mic.
All right. A few slides back, you showed a couple of commands for Spack. Yes, this.
Okay.
I was wondering, does it store the CPP flags that it used, or the CPU microarchitecture, or the specific GCC compiler that you specify here?
Oh, yeah. That's
Okay.
a great question. I think for the microarchitecture, there is stuff which is defined by the project, right? But for the compiler flags, I wouldn't say so. I think you might like override some defaults, but in the end, you're specifying these directly. So does that answer your question?
Well, I'm just thinking of the Gen 2 equivalent thing. So, for instance, I see a use flag like thing there, the plus threads, or the CPP flags. So, in Gen 2, when you do these kind of things, I think the idea is that those are recorded, so that later, if another package needs to have MPI leaks compiled with threading support, the dependency tree can resolve whether there is such a package or not. So I'm wondering whether these settings are ephemeral or stored as soon as you have installed MPI leaks.
I think, yes, I understand. I think they are stored, right? Once the MPI leaks package has been installed as a dependency and something else requires it,
yeah.
I would guess that definitely it's being used with thread support. So basically, like I mentioned, the Spack supports like when the user is not explicit, it basically like decides something for you, and if the threads is kind of like not specified as an anti-dependency, right? Then yeah, definitely it would work. Yeah. So.
I was wondering, are the builds, you mentioned that something from the host OS might leak in, are the builds in any way sandboxed and reproducible maybe even, or is that a completely separate problem?
Well, for the most part, I'm not quite sure. I think Spack has a concept of environments, right? So you would get like Spack lock and Spack YAML, which would basically create something like an sandboxed environment, right? But I'm not exactly sure whether it does not pollute the rest of the system, because Spack is initially designed to work parallel to existing package manager. So it directly installs packages into the system, which might be a problem because you're then polluting the global system. But obviously you could maybe create something, maybe, for example, set a different install directory or something like that. So.
Okay, thank you.
So one of the problems of using a new package manager is that the amount of packages available are, of course, not that high, and if the community doesn't pick up steam, of course, it may lag behind in important also security patches and so on. If I got it correctly, you're still trying to put a full image for the embedded device at the end. So what is the reason why you didn't use buildroot or Yocto at the end, which provide a very similar syntax also to what you're doing, and buildroot is also declarative to a point?
Yeah, that's a great question. Basically, we wanted these kind of like advanced features. For example, to specify each individual build time, compile time options, right? And we wanted this to be specified as a single scripting language, right? So that we can define not only packaging, not only configuration, but also how the image will be built and any kind of configuration that will be as part of it, right? Currently, it's a little bit difficult to do that in OpenWRT and other build systems, and we hope that this system will be much more flexible in that regard. So.
You mentioned that you had also looked into Nix and Geeks and so on. I'm wondering in which ways they didn't fit your use case and where Spack fits it better?
Great question. It was very close. Nix was definitely interesting for us, especially given how the community is quite large and how well developed it is. Basically, we identified that the Nix language, which was kind of like defined for Nix use case, to be much too complex for our needs. So we wanted something a little bit simpler, and this is why we found Spack, which is like I said, Python domain-specific language. So when you write package recipes, you're writing Python code instead of Nix code. But yeah, we would say we were very close, and we were also considering Nix as well. So.
I think just to pile on the why not use this or why not use use that. I have a transitive why not use this or why not use that question. So why did the Lawrence Livermore laboratory not use Portage? Is that in the paper? Do you know?
I wouldn't know directly. I mean, Gentoo is used for scientific work. I know that. But I would guess you would have to ask them why they didn't. Maybe they did. I think they maybe even did before, and they considered this to be some kind of improvement worthy of creating. So, yeah.
Right.
Who knows? Good question. Yeah.
Yeah. Sorry. The install the packages, right, that defined in these Python or at least Python-like language, right? Are you at all concerned about the security? The package manager will, of course, run as some sort of root user. So are you not concerned that a bad package or somebody injects a dependency which has some issue, or like what are your security concerns? Do you even have? Like,
I'm sorry.
Something?
Yeah, good question. But are you asking this from the point of building the system or actually actively using it? So, for example,
yeah,
we tried to.
Yeah, from the point of like a supply chain attack, right? Say somebody infects wherever you store your packages, I guess your package database, and injects some arbitrary Python, and then whenever you build your images, you'll have this malicious rootkit.
Yeah, I understand. Yeah, you're basically talking about like trying to ensure that the whole dependency chain is not compromised. There is a work we need to address in this regard, right? We were looking at creating something called it was like SDOM, basically like SBOM, right? Software bombs. Bombs are bill of materials. And this is basically like metadata for each individual package, which specifies where it has been fetched from, what's the source code, how has it been changed, and how it has been built, right? And this is basically like chained. I think Yocto actually has some kind of proof of concept of this model, right? And we are definitely interested in integrating this into the system because obviously this is important for some of our customers, right?
Thank you for your talk. Do you already have an idea how you are going to build the Linux kernel package? Are you going to publish all patches, all the source codes with the patches for the different hardware in some repository and build it directly from the Git branches, or other package managers do it like this, that they take some upstream release and have a separate patches directory? And what are your ideas on that?
Well, yeah, basically how it's currently works is basically that we would definitely want to have this system pull from the mainline kernel. So basically fetch mainline release and then have it built for individual platform. In some cases it's not possible right now, right? And then we basically push our own branches on GitHub and use those. I think that's okay, as long as we are actually doing branches and not patches and like out of tree stuff, so that should be okay. Most of this work is actually being done during the upstream process. So, for example, if we are waiting for something to be upstreamed, we simply push it to our online repository, fetch from that, and once this is complete, we basically move over to the mainline kernel. So, yeah.
And what are your ideas? I mean, there were several talks on how to secure such image deployments, like with
what will the resulting Replica One do if the network hardware has a TPM or something like this? And yeah, what are your ideas on this regard? Also, immutable images or all these new ideas we heard during the conferences. Yeah.
I think these are excellent concepts, especially given that we're actually using systemd exclusively, right? Basically, we heavily invested in this ecosystem. So basically, on access points, our kind of like current Gen 2 builds of Replica One, we use systemd. So we found it much more flexible because of the APIs and so on. We can directly interface with the system. But yeah, we basically can integrate and use the TPM as part of our image kind of like deployment, right? We're not currently doing that for Gen 2 because the packaging of the actual images is a bit involved. But with Spack, I think, and with this new concept, once we create like packages, kernel packages, because how it works in Gen 2 currently or before, basically we had like kernel being built as a separate part manually by the user using scripts. But recently, I think there has been some progress, and they have created actual kernel packages. So yeah, basically, the packaging process is where this needs to be addressed. But yeah, I think we are definitely interested in going in that direction to actually use the TPM. Obviously, given that we provide images for networking platforms. Okay, thank you everyone.